Adiabatic process is a type of thermodynamic process that occurs without transferring any heat energy between the thermodynamic system and the surroundings. Adiabatic process is a type of thermodynamic process that occurs without transferring heat energy between the thermodynamic system and the surroundings and its environment. Without transferring heat energy between the thermodynamic system, adiabatic process is a type of thermodynamic process that occurs without transferring heat energy between the thermodynamic system and its environment. For adiabatic change, heat energy under bracket Q remains constant. Heat energy under bracket Q remains constant and dq will be 0. That means change in heat energy of the thermodynamic system will be 0. And for adiabatic expansion, final temperature of the thermodynamic system will be T2 and final heat energy will be again Q1. Initial heat energy was Q1 and final heat energy will be again Q1 in this adiabatic expansion. For adiabatic expansion, P2 less than P1, V2 greater than V1 and T2 will be less than T1. For this adiabatic expansion, as temperature decreases, that's why final internal energy U2 will be less than U1. Here dq will be 0. That means no heat energy is being exchanged between the thermodynamic system and the surroundings. And for adiabatic process or change, PV to the power gamma equal constant, where gamma is the ratio of molar specific heat of the gas at constant pressure and volume. That's why gamma is equal to Cp by Cv, capital Cp by capital Cv, where capital Cp is the molar specific heat of the gas at constant pressure and capital Cv is the molar specific heat of the ideal gas at constant volume. For adiabatic change, dP by dV is equal to minus gamma P by V, where P is the pressure, V is the volume. That's why dP by dV subscript AD is minus gamma P by V. dP by dV subscript AD is the slope of adiabatic expansion or adiabatic change. dP by dV AD is equal to minus gamma into P by V, which is the slope of adiabatic curve. We know that dP by dV AD, that is slope of adiabatic curve, is gamma times of slope of isothermal curve. That is dP by dV AD is equal to gamma times of dP by dV iso. Therefore, dP by dV AD greater than dP by dV iso. That means slope of adiabatic curve will be greater than the slope of isothermal curve. Hence, what we can say, that is adiabatic curve is steeper than the isothermal curve, because adiabatic curve has greater slope with respect to the isothermal curve. And if we consider the expansion of an ideal gas, towards right hand side in the PV curve, in that case this will be the adiabatic curve, which is denoted by red color, and the isothermal curve is denoted by violet color. This is the adiabatic curve, which is steeper than the isothermal curve. Adiabatic curve denoted by red color is steeper than the isothermal curve. Now, specific heat of the gas is small c, which is 1 by m dq by dt, where m is the total mass of the ideal gas. Small c is the specific heat of an ideal gas, and we have to find the expression or value of specific heat of the ideal gas for adiabatic expansion or for adiabatic change. As dq equal to 0, no heat is exchanged between the gas and the surroundings. That's why small c will be equal to 0. That is the value of specific heat of an ideal gas. For adiabatic change or adiabatic expansion will be 0. Small c is equal to 0, which is the specific heat of an ideal gas in an adiabatic expansion or in an adiabatic change. Because no heat energy is exchanged between the gas and the surroundings, that's why amount of heat absorbed by the gas or rejected by the gas dq will be 0. And adiabatic change occurs suddenly. Adiabatic change occurs suddenly, and the adiabatic change occurs suddenly, and the ideal gas is placed in a cylinder with non-conducting walls. Adiabatic change occurs suddenly, and the ideal gas is placed in a cylinder with non-conducting walls. For adiabatic expansion, final pressure P2 less than initial pressure P1, final volume V2 greater than initial volume V1, final temperature T2 less than initial temperature T1, and final internal energy U2 will be less than initial internal energy U1. We know that change in internal energy du is n CVdt, and change in heat energy dq is n Cp dt. And in this adiabatic expansion, heat energy of the gas remains constant. That's why q equal constant. Work done in adiabatic expansion is W, which is P2 V2 minus P1 V1 divided by 1 minus gamma. Therefore, work done W will be equal to nR T2 minus T1 divided by 1 minus gamma. That is the work done in an adiabatic expansion of ideal gas. We'll have the expression W equal nR T2 minus T1 divided by 1 minus gamma. That is the work done by the gas in an adiabatic expansion. And also work done has another expression in this adiabatic expansion, that is W equal n CVdt. That means W equal n Cv under bracket T1 minus T2. Work done in adiabatic expansion has the expression W equal n Cv under bracket T1 minus T2, initial temperature minus final temperature. In adiabatic expansion, V2 greater than V1, final volume greater than initial volume. Therefore, change in volume dV will be positive. That means dV will be greater than 0, as change in volume dV equal to V2 minus V1. As V2 is greater than V1, that's why dV will be greater than 0. That means change in volume will be positive. Therefore, work done will be greater than 0, because work done has the expression P dV, integration P dV, where P is the pressure, dV is the change in volume. Therefore, NCV under bracket T1 minus T2 will be greater than 0. Therefore, T1 minus T2 greater than 0. Therefore, T1 will be greater than T2. T1 will be greater than T2. That's why T2 is less than T1. That means final absolute temperature of the gas T2 will be less than the initial absolute temperature of the ideal gas under bracket T1. T2 less than T1 means final temperature will be less than initial temperature. As final temperature is less than initial temperature, that's why temperature decreases in adiabatic expansion, and we can say that there will be cooling effect in an adiabatic expansion of an ideal gas. There will be cooling effect in adiabatic expansion of an ideal gas. There will be cooling effect in adiabatic expansion of an ideal gas. Now we shall discuss the examples of adiabatic process or adiabatic change. In the diagram, we have a cylinder, and that cylinder encloses an ideal gas with non-conducting walls and fitted with a frictionless pulley. Q1 is the initial heat energy of the ideal gas, and on the right hand side, T2 is the final temperature, U2 is the final internal energy, but heat energy remains constant as Q1. And due to expansion of the ideal gas, the piston moves upwards. That means there will be upward displacement of the frictionless pulley fitted with the cylinder enclosing the ideal gas. This is the direction of upward displacement of the piston due to adiabatic expansion, and this walls of the cylinder will be non-conducting. These walls are non-conducting walls, and this wall should be non-conducting so as to prevent any exchange of heat energy between the thermodynamic system and its environment. Now we can denote the final position of the piston due to adiabatic expansion of the gas, and final volume V2 will be greater than initial volume V1. Final pressure P2 will be less than initial pressure P1, and T2. Final temperature T2 will be less than initial temperature T1, but heat energy remains constant Q1 and Q1. And this is the adiabatic expansion of ideal gas enclosed by the cylinder with non-conducting walls. And here in this adiabatic expansion, obviously there will be no exchange of heat energy between the thermodynamic system and its environment. Here what we can write: no exchange of heat energy. No exchange of heat energy occurs in this adiabatic expansion. Therefore, first example of adiabatic process will be sudden expansion of an ideal gas. Sudden expansion of an ideal gas enclosed in a cylinder with non-conducting walls. Sudden expansion of an ideal gas enclosed in a cylinder with non-conducting walls so as to prevent the exchange of heat energy. Sudden expansion of ideal gas enclosed in a cylinder with non-conducting walls and isolated with a frictionless piston is an example of adiabatic expansion, is an example of an adiabatic expansion. Example of adiabatic cooling or adiabatic expansion, adiabatic cooling or adiabatic process. If the frictionless piston fitted with the cylinder is moved upwards, if the frictionless piston is moved upwards very quickly, comma, the gas enclosed in the cylinder with non-conducting walls expands adiabatically. The gas enclosed in the cylinder expands adiabatically, and the temperature of the gas decreases. Temperature of the gas falls or decreases. If the piston is moved upwards very quickly and the gas enclosed in the cylinder expands, temperature of the gas falls from T1 to T2, Hence it is an example of adiabatic cooling. Number 2 example is when an air mass descends over a mountain range. when an air mass descends over a mountain range. The pressure on the mass, the pressure on the mass, the pressure on the mass or parcel of air or the parcel of air increases. Parcel of air increases and its parcel's volume decreases. Parcel's volume decreases and its temperature increases. Hence, this is an example of adiabatic heating. This is an example of adiabatic heating. Number 3 example, the change in pressure. The change in pressure and volume of air columns due to propagation of sound wave in air is an example of adiabatic change. Is an example of adiabatic change. Adiabatic change is an example of adiabatic change. Number 4 example, oscillating pendulum in a vertical plane. Oscillating pendulum in a vertical plane is an example of adiabatic process.